The universe is 13.8 billion years old. Nothing can travel faster than the speed of light. So, the universe should be, at most, 13.8 billion light-years in radius, which means the entire universe, from one edge to the other, should be about 27.6 billion light-years across. Simple math. Light travels, time passes, distance equals speed, times time. Except there's a problem. The universe is actually 93 billion light-years across, not 27.6 billion, 93 billion. That's more than 3 times bigger than the age of the universe should allow. How is that possible? How did the edges of the universe get 46.5 billion light-years away from us when light, the fastest thing in existence, has only had 13.8 billion years to travel? It's like saying you got in your car, drove for exactly 1 hour at exactly 60 miles per hour, and somehow you ended up 180 miles from home. The math doesn't work. The physics shouldn't allow it. And yet, it's true. The universe is bigger than it has any right to be. And the explanation? It will fundamentally change how you understand reality. Because the universe didn't just break the rules. It found a loophole so elegant, so strange, so utterly mind-bending that when you finally understand it, you'll never look at space the same way again. By the end of this video, you're going to understand how the universe cheated physics, how it expanded faster than light, how space itself can grow while nothing actually moves, and how you, yes, you, exist in a cosmos so impossibly vast that your brain literally cannot comprehend it. But we're going to try anyway. Let's begin. Before we dive into the numbers, before we start throwing around billions and trillions and incomprehensible distances, I need you to understand something important. This isn't just trivia. This isn't some abstract fact you memorize and forget. This isn't about impressing people at parties with how many light years across the universe is. This is about understanding where you are. Right now, at this exact moment, you are sitting on a planet. That planet is orbiting a star. That star is one of hundreds of billions in a galaxy. That galaxy is one of trillions in the observable universe. And the observable universe? It's expanding, growing, getting bigger every single second. While you watch this video, the universe will expand by billions of miles in every direction. The farthest galaxies we can see are racing away from us at speeds that seem to violate everything you learned in physics class. Space itself is stretching, carrying galaxies apart faster than light can catch up. And here's what makes it profound. This isn't happening to some distant, abstract cosmos. It's happening to your universe, the one you live in, the one that contains everything you've ever known, everyone you've ever loved, every star you've ever seen. Understanding the size of the universe isn't just about big numbers. It's about understanding scale, about knowing your place in the cosmic hierarchy, about grasping, even for a moment, just how impossibly tiny you are, and yet how miraculous it is that you exist at all. Because when you truly comprehend how big the universe is, something changes. You realize that every human drama, every worry, every conflict is happening on a speck of dust orbiting an average star in an ordinary galaxy in an unremarkable region of space. And yet, on that speck of dust, consciousness emerged. You emerged. A pattern of atoms complex enough to look out at the universe and ask, how big is this place? That's not trivial. That's extraordinary. So, yes, we're going to talk about numbers. Distances measured in billions of light years. Structures so vast they span more than your mind can visualize. But we're also going to talk about what it means. What it means that you exist in something this incomprehensibly large. What it means that the universe has been expanding for 13.8 billion years and will continue expanding long after Earth, the Sun, and even the Milky Way are gone. What it means that we live in the brief cosmic moment when the universe is observable, when light from distant galaxies can still reach us before the accelerating expansion carries them beyond the horizon forever. This is your cosmic context, your address in the universe. And it's weirder, vaster, and more beautiful than you ever imagined. Here's how we're going to do this. We're going to start small, with you, with Earth, with things you can see and touch and comprehend. And then we're going to zoom out, step by step, scale by scale, each level approximately 1,000 to 1 million times larger than the one before. From Earth to the solar system, from the solar system to the nearest stars, from nearby stars to the Milky Way galaxy, from the Milky Way to neighboring galaxies, from galaxy clusters to superclusters, from superclusters to the largest known structures in the universe, and finally, to the edge, the boundary of the observable universe, the cosmic horizon beyond which light itself cannot reach us. At each step, I'm going to give you comparisons, visualizations, ways to make the incomprehensible at least slightly less incomprehensible. Because here's the challenge. Your brain evolved to understand distances measured in meters and kilometers, to track objects moving at speeds you can see, to comprehend timescales measured in years, maybe decades, maybe centuries if you really stretch your imagination. Your brain did not evolve to comprehend distances measured in billions of light years, to understand structures so large that light takes longer to cross them than the entire history of human civilization. So, we're going to build it up slowly. Give your brain time to adjust to each new scale before moving to the next. And at each step, I'm going to show you something impossible, something that reveals just how strange the universe really is. Because the universe isn't just big. It's big in ways that shouldn't be possible. Galaxies that are moving away from us faster than light. Regions of space that we will never see, no matter how long we wait, because the expansion of the universe is carrying them away faster than light can ever reach us. The universe is under no obligation to make sense, but it is under obligation to follow the laws of physics. And when you understand those laws, when you understand how space itself can expand, how cosmic inflation worked, how the universe grew from smaller than an atom to 93 billion light-years across in less than 14 billion years, you'll see that the impossible is actually inevitable. The universe had to be this big. The physics required it. And we're going to understand why. But first, we need to establish a baseline, a starting point. So let's start with something familiar, something you can relate to. Let's start with you. Right now, you're sitting somewhere, maybe at a desk, maybe on a couch, maybe lying in bed, watching this on your phone. You feel stationary, fixed in place. The world around you seems stable and still, but that's an illusion. Right now, at this exact moment, you are spinning with Earth's rotation at about 1,000 miles per hour, orbiting the Sun at 67,000 miles per hour, moving with the solar system around the galactic center at 514,000 miles per hour, and being carried with the Milky Way through space at 1.3 million miles per hour. You are moving through space at over 1 million miles per hour, and you can't feel it, because everything around you is moving with you. This is the first lesson about scale. Motion is relative, and the universe doesn't care about your perspective. From your point of view, you're still. But zoom out far enough, and you're hurtling through the cosmos at incomprehensible speeds. And we haven't even started talking about the expansion of space itself. That's coming. But first, we need to understand where you are. Your cosmic address starts here, on Earth. Let's zoom out and see where this journey takes us. Let's establish scale. You are made of atoms, about 7 times 10 to the power of 27 of them, to be precise. That's 7 octillion atoms. That's a 7 followed by 27 zeros. If you tried to count them, 1 per second, 24 hours a day, it would take you 200 billion years. That's 15,000 times longer than the current age of the universe. You are incomprehensibly complex, a temporary arrangement of atoms that somehow became conscious. That's already miraculous. But let's zoom out. You're standing on Earth, a rocky planet 12,742 kilometers in diameter. That's about 7,918 miles across. If you started walking at the equator and somehow could walk on water, walking 24 hours a day at 3 miles per hour, it would take you 110 days to circle the planet. Commercial jets fly at about 575 miles per hour. At that speed, circling Earth takes about 43 hours. But light? Light doesn't care about Earth's size. Light travels at 299,792 kilometers per second, 186,282 miles per second. At that speed, light circles the Earth 7.5 times every single second. Think about that. In the time it takes you to say 1 Mississippi, light has lapped the Earth 7.5 times. From light's perspective, Earth is tiny. Now let's get a sense of your scale compared to Earth. If you shrunk Earth down to the size of a basketball, about 24 centimeters in diameter, then you, a human being roughly 1.7 meters tall, would be about 3.2 micrometers tall in this model. That's 0.0032 millimeters. That's about 1/30 the width of a human hair. You would be invisible to the naked eye on basketball Earth. You'd need a microscope to see yourself. Mount Everest, the tallest mountain on Earth, 8,849 meters tall, would be 0.17 millimeters on basketball Earth. About twice the thickness of a sheet of paper. You could barely feel it with your fingertip. The deepest part of the ocean, the Mariana Trench, 11 kilometers deep, would be 0.21 millimeters. Also about the thickness of 2 sheets of paper. Earth is smooth at this scale. All our mountains and trenches, all our buildings and cities, all the geography we consider dramatic and significant. Invisible. Microscopic variations on a smooth sphere. And you? You're not even a bacteria on basketball Earth. You're smaller than that. Far smaller. This is the first real gut punch of cosmic scale. You are nothing compared to your own planet. A speck on a speck. But here's what makes it worse. Earth? Earth is nothing compared to what's out there. Watch this. Let's zoom out to the solar system. The Sun is 1.4 million kilometers in diameter, about 865,000 miles across. You could fit 109 Earths side by side across the Sun's diameter. In volume, you could fit 1.3 million Earths inside the Sun. And in mass, the Sun contains 99.86% of the solar system's total mass. Everything else, all 8 planets, all the moons, all the asteroids, all the comets, all the dust, all the gas, everything that isn't the Sun makes up less than 0.14% of the solar system's mass. Jupiter, the largest planet, contains 71% of that remaining 0.14%. Jupiter is 318 times more massive than Earth, and Jupiter is still a rounding error compared to the Sun. We are living on a rounding error of a rounding error. Now let's talk about distance. Earth orbits the Sun at an average distance of 150 million kilometers, 93 million miles. Astronomers call this one astronomical unit, or 1 AU. Light from the Sun takes 8 minutes and 20 seconds to reach Earth. When you see a sunrise, you're seeing the Sun as it was 8 minutes ago. Mars, the next planet out, orbits at 1.5 astronomical units. Light takes about 13 minutes to get there. Jupiter? 5.2 astronomical units. Light takes 43 minutes. Saturn? 9.5 astronomical units. Light takes 80 minutes, over an hour. Neptune, the farthest planet, orbits at 30 astronomical units. Light from the Sun takes 4 hours to reach Neptune. Think about that. Neptune is so far from the Sun that it experiences sunlight 4 hours old. When the Sun rises on Neptune, that light left the Sun 4 hours ago. And the edge of the solar system, the heliopause, where the solar wind stops and interstellar space begins, is about 120 astronomical units away. Light takes 16.7 hours to reach the edge. Let's put this in perspective. Voyager 1, launched in 1977, is the farthest human-made object from Earth. It's been traveling for 47 years at about 61,000 kilometers per hour, 38,000 miles per hour. In those 47 years, Voyager 1 has traveled about 24 billion kilometers. That's 160 astronomical units. It barely crossed the heliopause, the edge of the solar system, in 2012. After 35 years of travel, the solar system is so big that our fastest spacecraft, traveling for nearly half a century, has barely left it. Now here's the scale comparison. Remember basketball Earth? Let's use that scale for the solar system. If Earth is a basketball 24 centimeters across, then the Sun would be 26.5 meters in diameter. That's an 87-foot sphere, about as tall as an 8-story building. And Earth would orbit this 8-story tall Sun at a distance of 2.8 kilometers. That's 1.75 miles. Neptune would orbit at 56 kilometers, 35 miles away. The entire solar system, on this scale, would be 70 miles across. Imagine an 8-story building in the center, a basketball orbiting it 1.75 miles away, and the edge of the system 35 miles out. That's mostly empty space, vast distances with almost nothing in them. This is the second gut punch. The solar system is almost entirely nothing. Tiny objects separated by enormous voids. And you know what's worse? The solar system is a speck, because the distance to the nearest star is about to break your brain. The nearest star to our Sun is Proxima Centauri. It's 4.24 light-years away. A light-year is the distance light travels in 1 year. Since light moves at 299,792 kilometers per second, and there are 31.5 million seconds in a year, 1 light-year equals 9.46 trillion kilometers. That's 5.88 trillion miles. Proxima Centauri is 4.24 light-years away. That's 40.1 trillion kilometers, 25 trillion miles. Let me make this visceral. Light from Proxima Centauri takes 4.24 years to reach us. If Proxima Centauri exploded right now, vanished in a supernova, we wouldn't know for over 4 years. We'd keep seeing it in the sky, shining peacefully, completely unaware that it no longer exists. Now let's talk about how long it would take to get there. Voyager 1 is traveling at 61,000 kilometers per hour. At that speed, how long would it take to reach Proxima Centauri? 73,000 years. The fastest spacecraft ever built. the Parker Solar Probe, which has reached speeds of 700,000 kilometers per hour using the Sun's gravity, would still take 6,300 years to reach Proxima Centauri. With our current technology, interstellar travel is basically impossible. The distances are too vast. The timescales are measured in millennia. Here's the scale comparison that will make this click. Remember our basketball Earth model, where the solar system is 70 miles across? On that same scale, Proxima Centauri, our nearest neighbor, would be 75,000 kilometers away. That's 46,600 miles. That's almost twice the circumference of the actual Earth. If the solar system is 70 miles across, the nearest star is 46,600 miles away. Imagine standing in Los Angeles. The sun is an 8-story building. Earth is a basketball 1.75 miles away. Neptune is 35 miles out. And Proxima Centauri? It's another 8-story building in Thailand, on the other side of the planet. That's the distance between stars. The space between stars is void, almost perfect vacuum, less than 1 atom per cubic centimeter, the emptiest empty you can imagine. This is the third gut punch. There is far more nothing than something in the universe. Stars are rare, isolated, separated by distances so vast that even light takes years to cross the gaps. Our sun is alone in an ocean of darkness, with the nearest lighthouse years away. And this is just the beginning of understanding cosmic scale, because the Milky Way, our galaxy, contains 200 to 400 billion stars, each one separated from its neighbors by light years of empty space. Let's zoom out to the galactic scale and see what that looks like. The Milky Way galaxy is a barred spiral galaxy, approximately 100,000 light-years in diameter. 100,000 light-years from one edge to the other. Remember, 1 light-year is 9.46 trillion kilometers, so the Milky Way is 946 quadrillion kilometers across. That's 946 trillion kilometers. If you tried to drive across the Milky Way at highway speeds, 100 kilometers per hour, it would take you 1.08 trillion years. That's 78 times longer than the current age of the universe. The Milky Way contains between 200 and 400 billion stars. Let's use 300 billion as our estimate. 300 billion stars, each one a sun, many with planets, some potentially with life. Our sun is located about 26,000 light-years from the galactic center. We're in a minor spiral arm called the Orion Arm, about halfway out from the center to the edge. And we're moving, orbiting the galactic center at approximately 828,000 kilometers per hour, 514,000 miles per hour. At that speed, it takes about 225 million years to complete one orbit around the galaxy. That's how big the Milky Way is. It takes 225 million years just to orbit it once. Now here's the structure. The Milky Way isn't uniform. From our position inside the disk, we see the Milky Way as a band of light stretching across the sky. That band is our edge-on view of the galactic disk. We're looking through billions of stars, dust, and gas, all layered in a flat plane. If you could view the Milky Way from outside, from above or below, you'd see a beautiful spiral structure, arms curving out from a central bar, glowing with blue young stars and pink nebulae. But we can't see that view. We are stuck inside, seeing only the edge-on perspective. Now, for the scale comparison, if the Milky Way were the size of the continental United States, about 4,500 kilometers across, then the solar system would be the size of a quarter, a coin 24 millimeters across. Earth's orbit around the Sun, smaller than a grain of sand. Earth itself, microscopic, invisible. You don't exist at this scale. You're not even an atom on this model. You're far, far smaller than that. This is the fourth gut punch. Our entire solar system, sun, planets, everything we've ever physically explored, is nothing at the galactic scale. We are less than a pixel in a galaxy-sized photograph. But here's what's truly humbling. The Milky Way, it's average. Not particularly large, not particularly small, not particularly anything. It's just one of hundreds of billions of galaxies in the observable universe. Most are similar in size, some are larger, some are smaller. Our galaxy is unremarkable, ordinary, one of countless spiral galaxies scattered through space. And even the Milky Way is mostly empty space. Those 300 billion stars, they're separated by light years. The distances between them dwarf the distances within the solar system. If you removed all the stars from the Milky Way and compressed them together, no empty space between them, the entire galaxy would fit in a sphere about 4 light years across, smaller than the distance to Proxima Centauri. 99.9999999% of the Milky Way is nothing. Empty space, vacuum, void. This is a recurring theme. At every scale, the universe is mostly empty. Matter is rare. Structure is the exception, not the rule. And we've only just begun. Because the Milky Way, it has neighbors. Galaxies don't exist in isolation. They cluster together, drawn by gravity into groups and superclusters that span hundreds of millions of light years. Let's zoom out further, to the local group, to nearby galaxies, to structures that make the Milky Way look small. The journey is just beginning. We've traveled from you, made of 7 times 10 to the power of 27 atoms, to Earth, to the solar system, to the space between stars, to the Milky Way galaxy containing 300 billion suns. Each step was roughly 1,000 to 100,000 times larger than the previous. And at each step, you became smaller, more insignificant. A speck on a speck on a speck. But we're not done. Because galaxies themselves cluster into structures. And those structures cluster into larger structures. And the pattern continues, up and up, until we reach the edge of what we can observe. The Milky Way is just one galaxy in a cluster of about 80 galaxies called the local group. The local group is just one cluster in a supercluster called Laniakea, containing 100,000 galaxies. And Laniakea? It's just one supercluster among millions in the observable universe. Let's keep zooming out, to our galactic neighbors, to the structures that dwarf entire galaxies, to the cosmic web that organizes the universe on the largest scales. The journey continues. The Milky Way has a neighbor, and it's coming to kill us. Well, not you specifically. You'll be long gone. Earth will probably be long gone too. But in about 4 billion years, our galaxy is going to collide with the Andromeda Galaxy in one of the most spectacular cosmic events imaginable. But let's back up. What is Andromeda? Catalogue designation: M31. The Andromeda Galaxy is the closest major galaxy to the Milky Way. It sits 2.5 million light-years away. 2.5 million light-years. That means the light you see when you look at Andromeda. And yes, you can see it with your naked eye on a dark night, appearing as a faint smudge in the constellation Andromeda. That light left the galaxy 2.5 million years ago. When those photons began their journey toward Earth, our ancestors weren't even human yet. Homo habilis was just learning to use stone tools. Homo sapiens wouldn't evolve for another 2.2 million years. Agriculture was 2.49 million years in the future. Writing was 2.497 million years away. Everything you consider civilization was impossibly distant, and those photons just traveled through the void between galaxies, through space so empty there's less than one atom per cubic meter, for 2.5 million years, until last night when they entered your eye, struck your retina, and became a signal in your brain. You saw light that is older than humanity itself. Now let's talk about Andromeda's size. The Andromeda Galaxy is approximately 220,000 light-years in diameter. That's more than twice the diameter of the Milky Way. If the Milky Way is 100,000 light-years across, Andromeda is 220,000 light-years across, more than double. And in mass, Andromeda contains roughly 1.5 trillion solar masses. The Milky Way contains about 1 trillion solar masses. Andromeda is the bigger sibling in our galactic relationship. It contains approximately 1 trillion stars. 1 trillion stars. If you counted one star per second, 24 hours a day, it would take you 31,700 years to count all the stars in Andromeda. And each of those stars is a sun. Most have planets. Some of those planets might be habitable. Some might host life. Some might have civilizations looking up at their night sky, seeing our galaxy as a faint smudge, wondering if they're alone. But here's what makes Andromeda special and terrifying. Most galaxies in the universe are moving away from us due to cosmic expansion. Their light is redshifted, stretched to longer wavelengths by the Doppler effect. But Andromeda is blue-shifted. It's moving toward us at approximately 110 kilometers per second. That's 396,000 kilometers per hour, 246,000 miles per hour. Andromeda is rushing toward the Milky Way at 250,000 miles per hour, and there's nothing we can do to stop it. In about 4 billion years, give or take a few hundred million, Andromeda and the Milky Way will collide. Not a collision of stars. Galaxies are mostly empty space, remember? Direct stellar collisions will be incredibly rare. But a collision of galaxies. Two massive structures, each containing hundreds of billions of stars, passing through each other. Gravitational fields interacting, structures distorting. Gas clouds colliding and triggering explosive bursts of star formation. From Earth's perspective, if Earth still exists, if the Sun hasn't already expanded into a red giant and engulfed it, the night sky will transform. Andromeda will grow larger and larger over millions of years. Instead of a faint smudge, it will become a defined spiral, then a brilliant band across half the sky, then a chaotic swirl of stars filling the entire celestial sphere. The collision will be the most spectacular sky show Earth will ever experience. And it's inevitable. Already in progress, the galaxies are rushing toward each other at 110 kilometers per second, and gravity will not be denied. Here's the scale comparison that makes this real. Andromeda is 2.5 million light-years away. The Milky Way is 100,000 light-years across. That means Andromeda is only 25 Milky Way diameters away from us. Imagine if the Milky Way were the size of a dinner plate, 25 centimeters across. On that scale, Andromeda would be another dinner plate 6.25 meters away. That's about 20 feet. In cosmic terms, Andromeda is right next door. We're practically touching. This is the fifth gut punch. Even the nearby galaxies are millions of light-years away. The distances between galaxies dwarf the distances within galaxies. But Andromeda isn't alone. The Milky Way and Andromeda are part of a larger structure, a gravitationally bound group of galaxies called the local group. Let's zoom out and see the neighborhood. The local group is a collection of approximately 80 galaxies, all gravitationally bound to each other, occupying a region of space about 10 million light-years across. 10 million light-years. That's 94.6 quintillion kilometers. The three largest members are the Milky Way, approximately 300 billion stars, 100,000 light-years across Andromeda, M31, approximately 1 trillion stars, 220,000 light-years across Triangulum, M33, approximately 40 billion stars, 60,000 light-years across. These three spiral galaxies dominate the local group. They contain most of the mass, most of the stars, most of the structure. But surrounding them are dozens of smaller galaxies. Dwarf galaxies, irregular galaxies, satellite galaxies orbiting the larger ones, like moons orbiting planets. The Milky Way alone has about 60 known satellite galaxies. The largest are the Large and Small Magellanic Clouds, visible from the southern hemisphere as faint patches of light. These dwarf galaxies are being slowly consumed, torn apart by the Milky Way's gravity. Their stars are being absorbed into the Milky Way's halo. Galactic cannibalism is common. Most large galaxies grew to their current size by devouring smaller neighbors. The Milky Way is currently absorbing the Sagittarius dwarf elliptical galaxy, a process that's been ongoing for hundreds of millions of years. Streams of stars from this doomed galaxy wrap around the Milky Way like ribbons. In the future, the Milky Way will consume even more satellites, and eventually it will merge with Andromeda, creating Milkomeda, a giant elliptical galaxy that will dominate the local group. But here's what makes the local group interesting. It's isolated. The nearest galaxy group is about 10 million light-years away. That's roughly the same distance as the diameter of the local group itself. In our dinner plate model, where the Milky Way is a 25 centimeter plate, the local group would be a sphere 2.5 meters in diameter, and the nearest neighboring group would be another sphere 2.5 meters away. Galaxy groups are separated by voids, vast regions of space with almost no galaxies at all. But galaxy groups don't exist in isolation either. They cluster into even larger structures. The local group is part of the Virgo supercluster, a massive collection of galaxy groups and clusters spanning 100 to 10 million light-years. Wait, scratch that. Recent observations have revealed something even bigger. The local group isn't just part of the Virgo supercluster, it's part of an even larger structure called Laniakea. And Laniakea is where things get truly mind-bending. In 2014, astronomers published a groundbreaking map of galactic motion in our cosmic neighborhood. They tracked the movements of over 8,000 galaxies, measuring how they flow through space under the influence of gravity. What they discovered was stunning. All these galaxies, including the Milky Way, are flowing toward a common gravitational center, like rivers flowing toward the sea. They named this massive structure Laniakea, a Hawaiian word meaning immeasurable heaven. And it is immeasurable, or nearly so. Laniakea is approximately 520 million light-years in diameter. To put that in perspective, remember, Andromeda is 2.5 million light-years away. Laniakea is 208 times larger than the distance to Andromeda. If Andromeda's distance is 1 inch, Laniakea is 17 feet across. Laniakea contains approximately 100,000 galaxies. Each galaxy contains billions of stars. Each star might have planets. The numbers become meaningless. If the Milky Way contains 300 billion stars, and Laniakea contains 100,000 similar galaxies, then Laniakea contains roughly 30 quadrillion stars, and the total mass, approximately 100 quadrillion solar masses. That mass is spread across 520 million light years, organized into filaments and sheets and clusters, separated by vast cosmic voids. And all of it, is flowing toward a region called the Great Attractor. The Great Attractor is a gravitational anomaly located roughly 150 million light-years away from us, in the direction of the constellations Triangulum Australe and Norma. It's obscured by the disk of the Milky Way, so we can't see it directly. But we can measure its effect. Thousands of galaxies, including ours, are being pulled toward it at hundreds of kilometers per second. What is the Great Attractor? We're not entirely sure. It's likely a massive concentration of dark matter and galaxy clusters, but it's hidden behind the Milky Way's galactic plane, so observations are difficult. What we do know is that the Great Attractor itself is being pulled towards something even larger. The Shapley supercluster, a massive concentration of galaxies located 650 million light-years away. Think about that. We're not just orbiting our galaxy. We're not just moving with the local group. We're flowing through space on cosmic rivers of galaxies, pulled by gravitational structures hundreds of millions of light-years away. Your motion through the universe is determined by structures so vast you can't even see them all. Here's the scale comparison. If the entire Laniakea supercluster were compressed to the size of the United States, about 4,500 kilometers across, then the Milky Way would be about 900 meters across, about half a mile. The solar system? About 8 millimeters, smaller than a pencil eraser. Earth? Microscopic. Invisible. You don't exist at this scale, not even as a concept. This is the sixth gut punch. The structures that govern our galaxy's motion are so enormous that our entire galaxy becomes invisible when you zoom out far enough. But even Laniakea isn't the largest structure in the universe. There's something bigger, something so large it breaks the fundamental principles of cosmology. Something that shouldn't exist, but does. In 2013, a team of astronomers, analyzing gamma-ray bursts, made a discovery that shouldn't have been possible. They found a structure, a supercluster, or possibly a filament of superclusters, that measures approximately 10 billion light-years across. It's called the Hercules Corona Borealis Great Wall, and it's the largest known structure in the observable universe. To put this in perspective, the entire observable universe is 93 billion light-years in diameter. This structure is more than 10% of that. If the observable universe were a basketball court, 94 feet long, the Hercules Corona Borealis Great Wall would stretch 10 feet across. A single structure, one connected region. But here's the problem. It shouldn't exist. According to the cosmological principle, a fundamental assumption in cosmology, the universe should be homogeneous and isotropic on large scales. That means matter should be evenly distributed when you zoom out far enough. Small clumps? Fine. Galaxies, galaxy clusters, even superclusters. Expected. But structures larger than about 1.2 billion light-years? Theoretically impossible. The universe hasn't been around long enough for gravity to pull together structures that large. Think about it. Gravity works at the speed of light. Information about mass propagates at the speed of light. For a structure 10 billion light-years across to form, different parts of that structure would need to have communicated gravitationally for 10 billion years. But the universe is only 13.8 billion years old. And for the first few 100,000 years, matter was too hot and energetic to clump together at all. Realistically, the universe has only had about 13 billion years for large-scale structures to form. And even in that time, structures larger than about 1.2 billion light-years shouldn't have had time to coalesce. The Hercules Corona Borealis Great Wall is 8 times larger than that theoretical limit. It violates the cosmological principle. It challenges our understanding of how structure forms in the universe. It suggests that either our models are incomplete or there's something about cosmic evolution we don't understand. Some scientists question whether it's even a real structure. The evidence comes from gamma-ray bursts, powerful explosions that mark the deaths of massive stars. The bursts seem to cluster in a region roughly 10 billion light-years across. But gamma-ray bursts are rare and difficult to detect. The dataset is incomplete. There might be observational biases. It's possible the clustering is just a statistical fluke. Future observations, particularly from proposed missions like the Theseus satellite, will help determine whether the Hercules Corona Borealis Great Wall is a real, coherent structure or an artifact of incomplete data. But if it's real, and most astronomers think it probably is, then it's the largest known structure in the universe. And it's a reminder that the universe is weirder than our theories predict. Here's what makes it profound. We're looking at structures so large that light takes 10 billion years to cross them. Think about that. If you were at one edge of this structure and shined a flashlight toward the other edge, the light would travel for 10 billion years before reaching the other side. That's 72% of the current age of the universe. When that light finished its journey, the universe would be older than it is now. This is the seventh gut punch. There are structures in the universe so large that they operate on timescales comparable to the age of the universe itself. But even this, even a structure 10 billion light-years across, isn't the edge. We've zoomed out from you to Earth, to the solar system, to nearby stars, to the Milky Way, to the local group, to Laniakea, to the largest structures in the universe. And we still haven't reached the edge of what we can observe, because the observable universe is 93 billion light-years across, and we're only about halfway there. Let's keep going, to the cosmic horizon, to the edge of everything we can see, to the boundary beyond which light itself cannot reach us. The journey continues. We've traveled from galaxies measured in hundreds of thousands of light-years to superclusters measured in hundreds of millions of light-years, to structures measured in billions of light-years. At each step, the numbers became larger, the timescales became longer, the structures became more abstract. You've gone from something you can comprehend, galaxies, clusters of galaxies, to something almost impossible to visualize. Structures so large that light takes billions of years to cross them. But we're not done. Because everything we've discussed so far, the Milky Way, Andromeda, the local group, Laniakea, even the Hercules Corona Borealis Great Wall, all of it exists within a sphere 93 billion light-years across, the observable universe. And now, we need to talk about that number, about why it's 93 billion light-years and not 27.6 billion, about how space itself expanded faster than light, about the edge of what we can see and what lies beyond. This is where the impossible becomes inevitable. This is where we answer the question that opened this video. How can the universe be bigger than its age allows? Let's find out. We've traveled from you, 7 times 10 to the 27th atoms, to Earth, to the solar system, to the Milky Way containing 300 billion stars, to the local group, to Laniakea spanning 520 million light-years, to structures 10 billion light-years across. At each step, the numbers became incomprehensible. The distances became abstract. The timescales stretched beyond human intuition. But now, we need to address the question that opened this video. The paradox that doesn't make sense. the impossible math that somehow describes reality. The universe is 13.8 billion years old. Nothing can travel faster than the speed of light. So, logically, the farthest light could have traveled in 13.8 billion years is 13.8 billion light years, which means the radius of the observable universe should be 13.8 billion light years, and the diameter, the total distance from one edge to the other, should be 27.6 billion light years, double the age. Simple math. Except the observable universe is actually 93 billion light years in diameter. Not 27.6 billion, 93 billion. That's 3.4 times larger than it should be. How is that possible? Did light travel faster than the speed of light? No, that's impossible. Special relativity forbids it. Did the universe age faster than 13.8 billion years? No. We've measured cosmic microwave background radiation, observed the oldest stars, calculated the expansion rate. Every method confirms the universe is 13.8 billion years old. So, what's going on? Here's the confusion, and it's where most people's intuition breaks down. When we say the universe is 93 billion light years across, we're talking about how far apart objects are right now, their current distance. But when we say light has only had 13.8 billion years to travel, we're talking about how long ago the light was emitted. These are two different measurements, and the difference between them reveals something profound about the nature of space itself. Let me make this concrete with an example. Imagine a galaxy at the edge of the observable universe. The light from that galaxy was emitted 13.8 billion years ago, shortly after the Big Bang. That light has been traveling toward us for 13.8 billion years. You might think, okay, so that galaxy is 13.8 billion light years away. But no, that galaxy is now approximately 46.5 billion light years away. How? How did it get farther away while light was traveling toward us? Because space itself expanded while the light was in transit. Think about it like this. Imagine you're walking forward on a treadmill. You're moving forward at, say, 3 miles per hour, but the treadmill is moving backward at 5 miles per hour. From your perspective, you're walking forward. You're making progress. Your legs are moving. You're exerting energy. You're traveling. But from an outside observer's perspective, you're actually moving backward at 2 miles per hour because the treadmill is carrying you backward faster than you can walk forward. Now replace you with light and replace treadmill with space itself, and you've got cosmic expansion. Light travels through space at 299,792 kilometers per second. Always. That's the cosmic speed limit. Nothing moves through space faster than that, but space itself can expand faster than light can travel through it. And that's not a violation of relativity, because relativity says nothing can move through space faster than light. It says nothing about space itself expanding. Space isn't a thing that moves. Space is the fabric of reality, and that fabric can stretch. When we observe a distant galaxy, we're seeing light that left that galaxy billions of years ago. At the moment the light was emitted, let's say the galaxy was 1 billion light years away from us. The light starts traveling toward us at the speed of light. But while that light is in transit, crossing the void between that galaxy and us, space is expanding. The distance between us and that galaxy is growing. So by the time the light reaches us, that galaxy is no longer 1 billion light years away. It might be 2 billion light years away, or 5 billion, or 46.5 billion. if the light has been traveling since near the Big Bang. The light didn't travel 46.5 billion light years. It traveled through space that was expanding while it traveled. This is called comoving distance. It's the current, present-day distance to an object, accounting for all the expansion that's happened since the light was emitted. Here's the critical insight. Light from the most distant galaxies has traveled for 13.8 billion years. But those galaxies are now 46.5 billion light years away because space expanded during those 13.8 billion years. And since there are galaxies in every direction at that distance, the diameter of the observable universe is 93 billion light years, twice the radius. This isn't speculation. This isn't theoretical. We can measure this. We observe galaxies whose light has been traveling for over 13 billion years. We can measure their redshift, how much their light has been stretched by the expansion of space. From that redshift, we can calculate how much space has expanded since the light was emitted. And from that, we can calculate their current distance. The math works. The observations confirm it. The universe is 93 billion light years across because space has been expanding the entire time light has been traveling through it. But here's where it gets even stranger. Space isn't just expanding. It expanded much faster in the past than it does now. In fact, in the first fraction of a second after the Big Bang, space expanded so fast that regions of the universe were separated by distances greater than light could have traveled in that time. And that brings us to cosmic inflation. The expansion of space isn't constant. It hasn't been steady and predictable throughout cosmic history. In the very early universe, specifically during the first 10 to the power of minus 36 to 10 to the power of minus 32 seconds after the Big Bang, the universe underwent a period of exponential expansion called cosmic inflation. During inflation, space expanded by a factor of at least 10 to the 26th power in less than a trillionth of a trillionth of a trillionth of a second. Let me say that again. The universe grew by a factor of 100 million billion in a fraction of a second so small, your brain can't comprehend it. If you took an atom, about 10 to the power of minus 10 meters across, and inflated it by that same factor, it would become larger than the observable universe. That's how fast inflation was. And during inflation, space expanded faster than the speed of light. Far, far faster. Now, before you object, before you say, wait, I thought nothing can go faster than light, remember, objects can't move through space faster than light, but space itself isn't bound by that rule. Imagine a rubber sheet with dots drawn on it. If you stretch the rubber sheet, the dots move apart, but the dots themselves aren't moving. The sheet is stretching, carrying them along. That's what happens during cosmic expansion. Galaxies aren't flying through space away from each other. Space is expanding, and galaxies are being carried along for the ride. During inflation, space expanded so fast that regions separated by less than a millimeter became separated by billions of light years. Almost instantly. This sounds insane. And it is insane. But it solves several major problems in cosmology. The horizon problem. When we look at the cosmic microwave background, the afterglow of the Big Bang, we see that the entire universe has almost exactly the same temperature in every direction. 2.725 Kelvin everywhere we look, with variations of only a few millionths of a degree. But how can regions of space that are billions of light years apart have the same temperature? They've never been in contact. Light from one region hasn't had time to reach the other region. So how did they know to have the same temperature? Inflation solves this. Before inflation, the entire observable universe was tiny, smaller than an atom, small enough that all regions were in thermal equilibrium. They had the same temperature because they were in contact. Then, inflation happened. Space expanded exponentially, carrying those regions apart so fast that light couldn't keep up. Today, we see them as opposite sides of the sky, billions of light years apart, having never been in contact since inflation. But they were in contact before inflation. That's why they have the same temperature. The flatness problem. When we measure the geometry of space, we find it's flat. Not curved like a sphere, not curved like a saddle. Flat like a sheet of paper. But for the universe to be this flat today, it had to be incredibly, impossibly flat right after the Big Bang. Even tiny deviations from perfect flatness would have grown over time. Inflation solves this. Imagine inflating a balloon. When it's small, you can see the curvature, but inflate it to enormous size, and any small patch looks flat. Inflate the universe by a factor of 10 to the 26th power, and any curvature becomes undetectable. The monopole problem. Particle physics predicts that the early universe should have created magnetic monopoles, particles with only one magnetic pole, north or south, but not both. We've never observed one. Inflation solves this. If monopoles were created before inflation, they would have been spread so far apart by the exponential expansion that we'd never expect to find one in our observable universe. So, inflation isn't just wild speculation. It solves real problems. It makes predictions that match observations. And it explains why the universe is 93 billion light years across, even though it's only 13.8 billion years old. Because space expanded faster than light during inflation and has continued expanding, more slowly, but still expanding, ever since. Here's the timeline. At 10 to the power of minus 36 seconds after the Big Bang, inflation begins and space expands exponentially. By 10 to the power of minus 32 seconds after the Big Bang, inflation ends, and the universe has grown by a factor of 10 to the power of 26 or more, 380,000 years after Big Bang. Universe cools enough for atoms to form. Cosmic microwave background is emitted. 13.8 billion years after Big Bang. Today, universe has expanded to 93 billion light years in diameter. And here's what's eerie. The expansion is accelerating again. Not as fast as inflation, not even close. But about 5 billion years ago, the expansion rate began increasing. Something, we call it dark energy, though we don't know what it is causing space to expand faster and faster. In the far future, if this continues, galaxies will recede from us so fast that their light will never reach us. The observable universe will actually shrink from our perspective as more and more galaxies disappear beyond the cosmic horizon. But we're getting ahead of ourselves. Let's focus on the present, on the edge of what we can currently observe. Let's dig deeper into inflation, because it's the key to understanding why the universe is so much bigger than its age suggests. Inflation was proposed in 1980 by physicist Alan Guth to solve the horizon and flatness problems. Since then, it's become the leading theory for the very early universe. Here's what we think happened. We're talking about 10 to the power of minus 36 seconds. The universe was incredibly hot and dense. It was filled with quantum fields, including something called the inflaton field. Think of a field like an invisible energy that permeates all of space. Electric fields, magnetic fields, gravitational fields. These are all fields. The inflaton is similar, but it had a special property. It created a repulsive gravitational effect. Normally, gravity attracts. Mass pulls on mass. But the inflaton field created negative pressure, a kind of anti-gravity that pushed space apart. And when space started expanding, the inflaton field remained at roughly constant density, because as space expanded, more field energy was created. This created a feedback loop. Expansion creates more field energy, which causes more expansion, which creates more field energy. Exponential growth. Runaway expansion. During this brief period, space doubled in size every 10 to the power of minus 37 seconds or so. That means it doubled again, over and over, about 60 to 100 times in total. 60 doublings means expansion by a factor of 2 to the 60 power equals 10 to the 18th power. 100 doublings means expansion by a factor of 2 to the 100 power equals 10 to the 30 power. In reality, inflation probably expanded space by somewhere between 10 to the 26th power and 10 to the 100 power, depending on the model. We don't know exactly, but even the lower estimate is incomprehensible. Then, as quickly as it started, inflation ended. The inflaton field decayed, converting its energy into particles, quarks, electrons, photons. The universe was suddenly filled with hot, dense matter and radiation. This is what we call the hot Big Bang, the aftermath of inflation. From that point forward, the universe continued expanding, but much more slowly. No longer exponential, just steady Hubble expansion, driven by the initial momentum from inflation. But here's what inflation left behind: quantum fluctuations. During inflation, tiny quantum fluctuations in the inflaton field were stretched to cosmic scales. These fluctuations became density variations, regions slightly denser or less dense than average. Those tiny variations became the seeds for all structure in the universe. Galaxy clusters formed where the density was slightly higher. Voids formed where it was slightly lower. We can see these primordial fluctuations in the cosmic microwave background. The tiny temperature variations, millionths of a degree, correspond exactly to the density fluctuations predicted by inflation. Flat geometry. Inflation stretched space so much that any curvature became undetectable. That's why we measure the universe as flat today. Homogeneity, because all of space was once smaller than an atom, causally connected in thermal equilibrium. Inflation explains why the universe looks the same in every direction. And here's the profound part. Inflation predicts specific patterns in the cosmic microwave background. Specific ratios of temperature fluctuations at different angular scales. Specific amounts of polarization. And when we measured those patterns with satellites like WMAP and Planck, they matched inflation's predictions almost perfectly. Inflation isn't just a wild idea. It's a theory supported by observations. But it also creates a strange implication. If inflation happened here, it probably happened, and is still happening, elsewhere. In regions of space beyond our observable horizon, inflation might still be ongoing, creating new bubble universes constantly. Our observable universe might be just one bubble in an eternally inflating multiverse. But that's speculative. What we know is that inflation happened here, at least once, about 13.8 billion years ago. And it's the reason the observable universe is 93 billion light years across, instead of 27.6 billion. Space expanded faster than light, and it's legal, so let's define exactly what we mean by observable universe. The observable universe is the spherical region of space from which light has had time to reach us since the Big Bang. Its radius is approximately 46.5 billion light-years in any direction from Earth. Its diameter is approximately 93 billion light-years. Its volume is roughly 4 times 10 to the power of 80 cubic meters. But here's the critical point. Observable doesn't mean entire. The observable universe is just the part we can see, the part from which light has had time to reach us. Beyond that boundary, beyond 46.5 billion light-years, there's more universe, possibly infinite, possibly just more of the same. Galaxies, stars, planets, maybe even other civilizations. But we can't see it, and we never will. Because light from those regions hasn't had time to reach us yet, and because the expansion of space is accelerating, it never will reach us. Think about it. A galaxy that's currently 50 billion light-years away is beyond our observable horizon. Light from that galaxy has been traveling toward us since the Big Bang, but because space has been expanding, it hasn't reached us yet. You might think, just wait longer. Eventually, that light will arrive. But no, because the expansion is accelerating. Space is expanding faster and faster. That galaxy is receding from us at a speed greater than light. Remember, space itself can expand faster than light, and the distance is growing. Light from that galaxy is traveling toward us, but it's like swimming upstream, in a river that's flowing faster than you can swim. You're making progress through the water, but you're still moving backward relative to the shore. Eventually, that galaxy will cross what's called the cosmic event horizon, the boundary beyond which objects will never be observable, no matter how long we wait. Currently, the cosmic event horizon is about 16 billion light-years away in terms of comoving distance. Any light emitted from beyond that distance right now will never reach us, because the expansion of space will carry it away faster than it can travel toward us. Over time, as the expansion continues and accelerates, more and more galaxies will cross this horizon and disappear from view. In about 100 billion years, if the accelerating expansion continues, every galaxy outside our local group will have receded beyond the cosmic horizon. Future astronomers, if they exist, will look up and see only the stars in their own merged galaxy, Milky, by that point. They won't see distant galaxies. They won't detect cosmic microwave background. They'll have no evidence the universe is expanding. They might conclude they live in a small, static universe containing one galaxy surrounded by eternal darkness. And they'd have no way of knowing they're wrong. This is the humbling truth about the observable universe. We live in a brief cosmic moment when the universe is observable. When we can see distant galaxies, measure expansion, study the cosmic microwave background, and piece together the universe's history. That window is closing, slowly, on timescales of billions of years, but closing nonetheless. The observable universe is 93 billion light-years across today. But in the far future, it will effectively shrink as more and more of the cosmos recedes beyond our horizon. We're fortunate. We exist at a time when the universe reveals its secrets. But beyond what we can observe, beyond that 93 billion light-year sphere, there's more. So much more. And we'll never see it. We've answered the paradox. We've explained how the universe can be 93 billion light-years across, even though it's only 13.8 billion years old. Space itself expanded, faster than light during inflation, steadily ever since, accelerating for the past 5 billion years. Light hasn't traveled 93 billion light-years. Light has traveled through space that was expanding while it traveled. The observable universe is 93 billion light-years wide because That's how far apart objects have been carried by the expansion of space in 13.8 billion years. But now comes the even bigger question. How big is the entire universe? Not just the part we can see, but the whole thing. Everything that exists, whether observable or not. Is there an edge? Does the universe loop back on itself? Is it infinite? We're about to venture beyond the observable, into the realm of the unknown. Let's continue. We've established that the observable universe is 93 billion light-years across. But now comes the question that keeps cosmologists awake at night. How big is the entire universe? Not just the part we can see, but everything. The totality of existence, all of space, all of matter, all of structure, whether light from it can reach us or not. Here's the honest answer. We don't know. We might never know, because by definition, anything beyond our cosmic horizon is unobservable. We can't see it. We can't measure it. We can't detect it with any instrument, no matter how advanced. But we can make educated guesses based on what we do observe. First, let's consider the geometry of space. Cosmologists measure something called the curvature of the universe. Space can be curved in three possible ways: positive curvature, closed universe, like the surface of a sphere. If you travel far enough in one direction, you eventually return to your starting point. In this geometry, the universe is finite, but has no edge. It loops back on itself. The total size would be larger than the observable universe, but still finite. Maybe a few 100 billion light-years across. Negative curvature, open universe. Like the surface of a saddle, space curves away from itself. In this geometry, the universe extends infinitely in all directions. There is no edge, no boundary, no outside. Just infinite space containing infinite galaxies. Zero curvature, flat universe. Like a sheet of paper extended infinitely. Space is perfectly flat with no curvature. This also implies an infinite universe, unless there's some exotic topology we haven't detected. So which is it? Based on measurements from the Planck satellite, the Wilkinson microwave anisotropy probe, and other cosmic microwave background experiments, the universe appears to be flat, to within about 0.4% precision. That means either 1. The universe is truly infinite, extending forever in all directions, or 2. The universe is so large that its curvature is undetectable within our observable horizon, like how Earth appears flat when you're standing on it, even though it's actually a sphere. If the universe is flat and infinite, then there are infinite galaxies, infinite stars, infinite planets. Everything that can happen, given enough space and time, does happen somewhere, including infinite copies of you reading this exact sentence. That's philosophically disturbing, but mathematically consistent. Now, there's another approach to estimating the universe's size: Bayesian analysis. In 2011, cosmologists used a statistical method called Bayesian model, averaging to estimate the minimum size of the universe based on inflation theory and observations of the cosmic microwave background. Their conclusion: the universe is at least 250 times larger than the observable universe. At least. That would make the total diameter at least 23 trillion light-years. That's 23 trillion light-years. But that's a lower bound. The universe could be far larger. It could be infinite. Think about what this means. The observable universe, 93 billion light-years across, containing 2 trillion galaxies, represents less than 0.001% of the total universe if these estimates are correct. Less than 1,000%. Everything we've observed, every galaxy mapped, every star catalogued, every planet discovered, is an infinitesimally small sample of what exists. If you took all human knowledge, everything we've learned about the cosmos through telescopes, satellites, mathematics, and physics, it would be like examining a single grain of sand and trying to understand all the beaches on Earth. We are profoundly, cosmically ignorant. But it gets stranger, because if the universe is infinite, or even just very, very large, then probability suggests something bizarre. Exact copies of you exist elsewhere. Not similar people. Not people who resemble you. Exact duplicates. Atom for atom identical copies, living identical lives, making identical choices, having identical thoughts. Here's why. There are only so many ways atoms can arrange themselves in a human-sized volume. The number is enormous, roughly 10 to the power of 10 to the power of 70. But it's finite. If space is infinite, and matter is distributed roughly uniformly, which observations suggest, then every possible arrangement of atoms exists somewhere, including arrangements identical to you, right now, reading this. Including arrangements identical to you making every possible choice you could ever make. There's a version of you who chose a different career, a version who lives in a different country, a version who made different mistakes, different triumphs, different decisions. And if space is truly infinite, there are infinite copies of each version. This isn't science fiction. This is a straightforward consequence of infinite space plus finite possible arrangements. It's called the infinite universe, or quantum immortality problem in philosophy. And it's deeply weird. But here's the kicker. Even if those copies exist, we'll never encounter them. They're beyond our cosmic horizon, beyond the observable universe, separated from us by distances so vast that light will never bridge them. They exist in the unobservable universe, the part that's real, that's out there, that contains matter and galaxies, and possibly life, but that we can never, ever see. This is the eighth gut punch. The universe you can observe is almost certainly a tiny, tiny fraction of what actually exists, and most of reality is forever hidden from you. But wait, it gets bigger. Because some versions of inflation theory predict something even more mind-bending than an infinite universe, a multiverse. Here's the idea. Inflation doesn't just happen once. It happens constantly, eternally, in a process called eternal inflation. Remember, inflation is caused by the inflaton field, a quantum field that creates exponential expansion. In most regions of space, this field eventually decays, inflation ends, and you get a pocket universe like ours. A hot Big Bang followed by normal expansion. But in some regions, inflation doesn't end. The field remains high energy, and those regions continue inflating exponentially. And within those inflating regions, random quantum fluctuations can create more pockets where inflation ends, creating more pocket universes. This process continues forever. Infinite inflation, creating infinite pocket universes, each with its own Big Bang, its own laws of physics, possibly, its own structure. Our observable universe, 93 billion light-years across, would be just one pocket, one bubble, in an infinite, eternally inflating multiverse. And here's where it gets truly strange. Each pocket universe might have different physics. In our universe, the electron has a specific mass. The speed of light is 299,792 kilometers per second. The strength of gravity is defined by Newton's gravitational constant. But in another pocket universe, these values might be different. Electrons might be heavier. Light might travel faster. Gravity might be stronger. Most of those configurations wouldn't allow stars to form, or atoms to exist, or chemistry to happen. They'd be sterile, lifeless, boring. But some, like ours, would have the right parameters for complexity, for galaxies and stars and planets and life. Our universe, with its specific physics, its 93 billion light-year observable region, its 2 trillion galaxies, is just one configuration among 10 to the 500. Now, before you dismiss this as wild speculation, let me be clear. We have no direct evidence for the multiverse. None. We can't observe other universes. By definition, they're beyond our cosmic horizon, causally disconnected from us, forever unobservable. But eternal inflation is a natural prediction of inflation theory. If inflation happened once, it probably happened many times. And if it happened many times, it's probably still happening in regions beyond our horizon. Cosmologists debate whether the multiverse is even science. If you can't observe it, can't test it, can't make predictions about it, is it physics or philosophy? But here's the thing. Even if the multiverse exists, it doesn't change anything for us. We live in this universe, with these physical laws, in this pocket of reality where stars form, planets coalesce, and conscious beings evolve. Whether there are infinite other universes with different physics doesn't affect our reality. It's interesting, humbling, mind-expanding, but ultimately, we're stuck here. The observable universe, our observable universe, is still 93 billion light-years across, still contains 2 trillion galaxies, still operates according to the laws of physics we've measured. That's the reality we can study. That's the cosmos we inhabit. Everything else, the unobservable universe, the multiverse, the infinite configurations of matter and energy beyond our horizon, is speculation. Informed speculation based on solid physics, but speculation nonetheless. So let's return to what we know, to what we can measure. Let's talk about the numbers, the actual, quantifiable scale of the observable universe. Because even limiting ourselves to what's observable, the numbers are incomprehensible. Let's try to wrap our minds around the scale of the observable universe with actual numbers. 2 trillion galaxies in the observable universe. If you counted one galaxy per second, 24 hours a day, it would take you 63,000 years to count them all. But galaxies aren't the endpoint. Each galaxy contains stars. The average galaxy contains about 100 billion stars. Some have more, some have less. But 100 billion is a reasonable average. That means the observable universe contains approximately 10 to the power of 24 stars. 1 septillion stars. To put that in perspective, there are roughly 10 to the power of 18 grains of sand on all of Earth's beaches. Every beach, every desert, every sandy surface on the planet. The universe contains 1 million times more stars than Earth contains grains of sand. For every grain of sand on every beach on Earth, there are 1 million stars in the universe. The universe is 13.8 billion years old. This energy is equivalent to the sun shining for a time period 100 billion trillion times longer than the current age of the universe. These numbers stop meaning anything. They're abstractions, symbols on paper. Your brain can't visualize 10 to the power of 80 atoms. It can't comprehend 10 to the power of 24 stars. It can't grasp 10 to the power of 53 kilograms. But here's what you can grasp. You exist within this. You are part of this incomprehensible scale. You, made of 7 times 10 to the power of 27 atoms, are a tiny temporary pattern in a cosmos containing 10 to the power of 80 atoms. You are less than a rounding error, less than a speck, less than a whisper in the vastness. And yet, you are the part that's conscious, the part that can look up, see stars, measure distances, calculate masses, and comprehend, even dimly, the scale of what you're part of. The universe is incomprehensibly large, but you're the part that knows it. We've traveled from Earth, 12,742 kilometers across, to the observable universe, 93 billion light-years across. We've confronted numbers that break comprehension. Distances measured in billions of light-years, galaxies counted in trillions. We've learned that the observable universe is probably just a tiny fraction of the total universe. That beyond our cosmic horizon, there's more, possibly infinite, space containing more galaxies, more stars, more worlds. We've considered the possibility that our universe is one pocket among infinite others in an eternally inflating multiverse. And we've realized that even asking, how big is the universe, might be the wrong question, because big is relative, and the universe might not have an edge, a boundary, or a size at all. But now we need to bring this home. We need to talk about what this means, not scientifically, not mathematically, but personally. What does it mean that you exist in something this vast? What does scale teach us about significance, about meaning, about our place in the cosmos? Let's finish this journey where it matters most, with you. We've reached the limits of what we can know. The observable universe is 93 billion light-years across. We've measured it, mapped it, catalogued 2 trillion galaxies within it. But beyond that boundary, we're guessing, extrapolating, speculating based on physics and mathematics, but ultimately confronting the limits of observation. We can't see beyond our cosmic horizon. We never will. The expansion of space, accelerating under the influence of dark energy, ensures that more and more of the universe will forever remain hidden from us. And here's what's humbling. Even within our observable sphere, we're profoundly ignorant. We've mapped 2 trillion galaxies, but we don't know what most of the universe is made of. Dark matter makes up 27% of the universe's mass-energy content. We know it exists because we can measure its gravitational effects on galaxies and galaxy clusters, but we don't know what it is. Not a single dark matter particle has ever been directly detected. Dark energy makes up 68% of the universe's mass energy content. It's causing the expansion of space to accelerate. But we have no idea what it is. Is it a property of space itself? A quantum field? Something else entirely? Normal matter, atoms, the stuff you and I are made of, the stuff stars and planets are made of, makes up only 5% of the universe. 5%. Everything we can see, touch, measure directly, everything in the periodic table, every element forged in stars, is less than 5% of what exists. The rest? Mystery. We live in a universe where 95% of its content is invisible, undetectable except through its gravitational influence, and completely unknown to us. We've sent spacecraft to the edge of our solar system. We've photographed galaxies billions of light-years away. We've measured the cosmic microwave background to millionths of a degree. We've detected gravitational waves from colliding black holes, and yet we don't know what most of the universe is. This is the 9th gut punch. We are cosmically ignorant. We've barely scratched the surface of understanding, and the more we learn, the more we discover how much we don't know. But here's what makes it bearable, what makes it beautiful, even. We know that we don't know. We're aware of our ignorance. We're actively working to reduce it. 500 years ago, humans didn't know galaxies existed. We thought the Milky Way was the entire universe. 100 years ago, we didn't know the universe was expanding. We thought it was static and eternal. 50 years ago, we didn't know about dark energy. We thought the expansion was slowing down. Every generation of astronomers discovers something that fundamentally changes our cosmic perspective, and every discovery reveals new mysteries. The edge of knowledge isn't a wall, it's a horizon, and horizons keep moving as we approach them. We'll never know everything. The universe is too large, too old, too complex. Some questions, like what happened before the Big Bang, or what's beyond our cosmic horizon, might be fundamentally unanswerable. But that's okay, because the journey of discovery, the process of asking questions, making observations, testing theories, expanding our understanding, is what gives meaning to our existence. We are the universe trying to understand itself, and even if we never fully succeed, the attempt is worth making. So here we are. At the end of this journey, we've traveled from you 7 times 10 to the power of 27 atoms to the observable universe, 93 billion light years, 2 trillion galaxies, and 10 to the power of 80 atoms. We've answered the question, how big is the universe? Observable universe, 93 billion light years in diameter. Total universe, unknown, at least 250 times larger, possibly infinite. We've explained the paradox. The universe is bigger than its age because space itself expanded faster than light can travel through it. We've confronted our cosmic insignificance. You are incomprehensibly small compared to the vastness of space. But we've also confronted our cosmic significance. You are the part of the universe that's conscious, that knows, that matters. So, what do you do with this information? Here's what I suggest. First, embrace the scale. Don't shy away from it. Don't pretend you're bigger than you are. You're tiny. Accept it. Let it humble you. Second, embrace your significance. You're tiny, yes, but you're conscious. You're the universe experiencing itself. That's extraordinary. That's rare. As far as we know, consciousness might be the rarest thing in the cosmos. Third, look up. Tonight, go outside. Look at the stars, not just glancing. Look. Let your eyes adjust. Find the Milky Way if you're away from city lights. Find Andromeda, that faint smudge containing 1 trillion suns. Remind yourself that you're not just on Earth. You're in space, riding a planet that's orbiting a star, that's orbiting a galactic center, that's being pulled toward a great attractor in a supercluster that's part of an observable universe 93 billion light years across. You're part of this, not separate from it, part of it. Fourth, appreciate the moment. You exist in the brief cosmic window when the universe is observable, when light from distant galaxies can still reach us, when we can measure, study, and comprehend the cosmos. In the far future, trillions of years from now, galaxies will have receded so far that future observers won't know the universe is anything more than their local cluster. They'll have no evidence of expansion, no cosmic microwave background, no way to discover the Big Bang. But you live now, when the universe reveals itself, when knowledge is possible. That's a privilege. Use it. Fifth, share the wonder. Tell someone about Andromeda, about Laniakea, about the 93 billion light years, about the paradox of space expanding faster than light. Wonder isn't diminished by sharing it. It's amplified. The universe is vast beyond comprehension, cold, mostly empty, operating on timescales and distance scales that make human life seem absurdly brief and small. But it's also beautiful, structured, comprehensible. governed by laws we can discover and understand. And you, tiny, temporary, fragile, you get to be here. You get to know this. You get to look up at a sky full of stars and know that each one is a sun, that those suns are grouped into galaxies, that those galaxies are organized into superclusters, that all of it exists in a cosmos 93 billion light-years across. You are impossibly lucky. You are impossibly small. You are impossibly significant. All three are true simultaneously. The universe is 93 billion light-years across, and you are here at the center of your own observable sphere, looking out at it all. That's not nothing. That's everything. If you've made it this far, thank you. We've journeyed from Earth, 12,742 kilometers across, to the observable universe, 93 billion light-years across. We've traveled through the solar system, past nearby stars, across the Milky Way containing 300 billion suns, beyond the local group, through Laniakea with its 100,000 galaxies, to structures spanning billions of light-years, finally reaching the cosmic horizon 46.5 billion light-years away in every direction. We've confronted the paradox: how can the universe be 93 billion light-years across if it's only 13.8 billion years old? And we've understood the answer. Space itself expanded, faster than light during inflation, steadily ever since, carrying galaxies apart, making the universe larger than time alone would allow. We've learned that the observable universe is probably just a tiny fraction of the total universe. That beyond our horizon, there's more, possibly infinite, space containing more galaxies, more stars, more worlds we'll never see. We've considered the multiverse, the possibility that our universe is one bubble among infinite others, each with its own physics, its own story. And we've returned to what matters. You, here, now, part of this vast cosmos, tiny but conscious, insignificant but meaningful. Subscribe if you want more journeys through the cosmos, more paradoxes explained, more perspectives that change how you see reality. Comment below. Which scale broke your brain? Was it the Milky Way, Laniakea, the 93 billion light-years, 10 to the power of 80 atoms? Tell me where your mind gave up trying to visualize. Share this video with someone who needs cosmic perspective, someone stressed about small problems, someone who's forgotten how extraordinary it is just to exist. And tonight, definitely, go outside and look up. Find the North Star if you're in the Northern Hemisphere. Find the Southern Cross if you're in the South. Find the Milky Way if you're away from cities. Those aren't just pretty lights. They're stars, suns like ours. Some larger, some smaller. Some with planets. Some possibly with life. And they're part of a galaxy 100,000 light-years across. In a local group 10 million light-years across. In a supercluster 520 million light-years across. In an observable universe 93 billion light-years across. You're looking at your universe, your cosmic home, your address in the vastness. Remember where you are. Remember how big it is. Remember how lucky you are to be here, now, conscious and aware. The universe is 93 billion light-years across, and tomorrow it'll be slightly bigger. Look up tonight.